Greetings, this is Mr. Garwood with our continuing video series on Calculus 2nd edition by Briggs, Cochran, and Gillette. In our last 3 or 4 videos, we've been focusing on the idea of the derivative telling me the slope of a tangent line at a particular point, and we've been focusing on how do I evaluate that slope at that point. And what I want to look at in this video is the derivative as a function. And so my argument here is if I have some arbitrary function, I could find, as we have in the last few videos, I could find a tangent line here. And we'll call this point C. And I might find another derivative here. We'll call this point B. And we could find, a derivative here. We could use all those rules. We'll call this point A. Well, the idea here is, well, if I find the derivative at every point, so if every x has a slope of the tangent line, and it has to be unique. There's only one tangent line anywhere. Then is it dy dx a function? Well, every point has an output. Every point has a slope for its tangent line. There's only one tangent line, so it's a 1-to-1 correspondence there. Well, and that's not necessarily true. There are points that could have the same slope. But couldn't I argue that that's a function? And then the question is, well, how do I evaluate that function? Now, and I kind of hinted at that in some of our earlier videos, but in our previous video we looked at f of x equals 2x cubed minus 5. Okay. Well, and what we did was we said when x is 3, and we evaluated that, but in that first example when I did the definition of the derivative, I actually plugged 3 in at the end, not at the beginning. Huh. That's an interesting conundrum, Mr. Garwood. Well, so we defined dy dx to be the limit as the change in x goes to 0 of the change in y over change in x, which is really just saying the slope of the tangent line. So this is slope of the tangent line because these are all the same. And we also said that we could also evaluate that as f prime of some number. Well, here, what if I don't tell you the point? What if I don't care what x value it is? What if I just say, hey, look, let's find the derivative. Okay, so here we go. So dy dx for this bad boy, and I can come over and just say that that's y, is the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, that's the limit h goes to 0 of 2 times x plus h cubed minus 5 minus 2x cubed minus 5 all over h. Well, just like we did before, I'm going to come over here and I'm going to say, well, -5 minus -5 is 0. No problems there. And then I'm going to have to do that thing where I've got to expand this bad boy out. Now, I'm actually going to be careful here, and I'm going to go ahead and pull out the 2, as we did in the other example. Everything on top was multiplied by 2, so I just factored out a 2, and using my limit rules I took it outside. And this thing gives me x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed, because these two came out, and that's all over h. Well, x cubed minus x cubed is 0, and I'm left with this. So I've got 2 times the limit. H goes to 0. Now I'm going to go ahead and factor out an h as I do this. So I'm going to say h times 3x squared plus 3xh plus h squared over h. Now, we're back to that weird rational function thing where I know that I can't plug in 0, but if I ignore the point where h is 0 and I look where everything else around it is going on, we're fine. H's cancel. So that's double the limit as h goes to 0, 3x squared plus 3xh plus h squared. Now, this is a polynomial, and our limit rules for polynomials say that I just plug in h for that polynomial. Well, if I do that, so that's double 3x squared. Well, there's no h, so I don't have to do anything there. Plus 3x times 0 plus 0 squared. Well, anything times 0 is 0, so those two go away, and what I'm left with is 2 times 3x squared, which is really just 6x squared. So dy dx is 6x squared. Well, Mr. Garwood, that's just another polynomial. It's not a very exciting one. It's just a stretched parabola, but that's a function. This is a function. And so what I've really done is, instead of evaluating when x is 3 and when x is negative 2, when x is pi, when x is e squared, when x is, I took all of those values and I did it all at once. And at the end of the day, if you say, hey, I need to know this tangent line at 3, I just plug in 3 for x here. And that's where this Lagrange notation that I introduced in our previous video comes in. I just have to plug in a value here. This is a function. The derivative is a function for the original function. So it works exactly the same way. You plug in an x, you get a y out. It just happens that y is not a function output. That y is the slope of the tangent line of another function. I think that's kind of neat, that this whole thing just becomes another function. And we can graph it. We can do anything else that we want to this function. Spoilers, we can actually take the derivative of the derivative. And what I want to notice here is, and actually no, we're gonna leave graphing for another day. But noticing here, the derivative is a function. That was the whole point of our video today. I hope you have found this video useful, and good luck as this course continues.